All right, you guys, we have two small sections that we're going to cover today. Free fall and then motion on an inclined plane. So we're going to start out with free fall. So let's just start by talking about it, all right? It's the motion of an object moving only under the influence of gravity. There is nothing else affecting it. So if you've asked me about air resistance, we're not dealing with it yet. That's still like 4 chapters in the future we'll deal with air resistance, but not right now. So we're gonna look at free fall as if it's occurring within a vacuum. So nothing else is affecting it. All the air is sucked out. It's just this one object and it's falling. Like this pin. Free fall, okay? Now, you might be wondering who discovered any of this information we're about to learn. It was actually Galileo. In the 17th century, he was the first person to make any detailed measurements regarding falling objects. It's actually believed that he would sort of drop things off of that Leaning Bell Tower of that cathedral in Pisa, and he would sort of take measurements of different weights as they would fall, like how long it took them to fall to the ground, things like that. Historians really haven't been able to say if this is true or not, but either way, Galileo is responsible for what we're about to learn. So we know 2 things, all right? One is that if we drop 2 objects from the same height, as long as we neglect air resistance, they're gonna hit the ground at the same time going the same speed. So it would be like if I had my calculator and a set of Post-it notes, and I dropped them both. They should hit the ground at the same time going the exact same speed. So that's one of the things we know. The other thing we know is that when we have 2 objects in free fall, regardless of their mass, regardless of their shape, their size, anything, they always have the same acceleration. And what we call that acceleration is acceleration free fall. Okay, acceleration free fall. Now, what acceleration free fall is equal to is 9.80 meters per second squared downward. Okay, because it's just falling through the air. It's in free fall. The acceleration is the same for everything in free fall, okay? The magnitude is known as the free fall acceleration, which we call G, which you guys saw the other day in your problem set, and I told you it was equal to 2.80 meters per second squared. You'll notice that that's negative. You'll notice that that's positive. G is always positive. It is just a magnitude, all right? We, however, when we're doing free fall, okay, our acceleration in the y direction of free fall is equal to the acceleration of free fall, which is equal to negative g, which is equal to negative 9.80 meters per second squared. So g itself is just a magnitude that we have in physics. It itself is not negative, but when we're in free fall, it becomes negative because we assume up to be the positive direction and down to be the negative direction. Also, G is only equal to 9.8 meters per second squared on Earth. If you go to any other planet, it's going to be different, unless it's identical to Earth in some way. Then it would be the same. But all the planets that we know of have a completely different free fall acceleration, a different G. So let's look at an example with this, okay? So we're going to talk about a falling rock. So we have a rock, and it's going to be dropped from a 20-meter tall building, okay? So down here we'll have 0 meters. Up here we'll have 20 meters. And this is where your little rock friend is, okay? He's up at 20 meters, and he's about to get dropped. So he has an initial position, an initial velocity, and an initial time. You'll notice that now for position, I'm using a y, And that's because previously we're on the X plane, now we're on the Y plane. So anything that's going up and down is considered to be on the Y plane, okay? When it falls, it's gonna have that free fall acceleration. So it's gonna be accelerating downwards. And it eventually is going to end up at 0 meters. What we wanna know is what is the impact velocity of the rock? So what velocity is the rock going when it hits the ground? The answer is not 0. People always say it's 0. It's not 0, okay? The impact velocity is not 0. So we're going to use one of the equations we learned previously, which is that our final velocity squared is equal to our initial velocity squared. And I know we learned 2a delta x, but we can replace that with 2a delta y, because now, like I said, we're in the y plane. And we're solving for our final velocity. Thankfully, this is a pretty easy switch up of the equation. All we're going to have to do is take the square root of each side. So we're going to get our final velocity is equal to the square root of our initial velocity plus 2a delta y. Okay? What do you think our initial velocity is? If I'm holding something and I'm about to drop it, what velocity is it going in my hand? It's going to be going 0 meters per second, all right? So our initial velocity is going to be 0. So we can get rid of that, and we'll have that our final velocity is equal to the square root of 2a delta y. All right, we know that our acceleration is the acceleration of free fall, which we just learned is going to be negative 9.8 meters per second squared. And if our initial position is 20 and our final position is 0, our displacement, our delta y, would be equal to final minus initial, which means that it's going to be negative 20 meters, okay? Negative 20 meters is our displacement. So when we plug this in, we're going to have that our final velocity is equal to the square root of 2 times negative 9.8 meters per second squared times negative 20 meters. All right? When you type that into your calculator, what do you get? My hope is that you get that your final velocity is equal to negative 19.79 meters per second. Which it makes sense that our velocity is negative, right? Because it would have been positive if it were going up, but it's coming down. And if it's coming down, it is in a negative direction, so our velocity should be negative. All right, you guys, so that was the only example I wanted to do with you on this video about free fall. I have another one I want to do in person that's a little bit more in depth so we can talk through it. But now we're going to move on to section 2.6, motion on an inclined plane, okay? So let's look at an example of an inclined plane. Sort of like a ramp, right? We've got a theta, and then let's say we have something and it's on its way down the inclined plane, okay? And we're gonna look at these little dots like it's the velocity, all right? So what happens is maybe it starts from rest, and as it goes down, it's gonna keep getting faster and faster because it's gonna have some sort of acceleration acting on it, sort of like when we were in free fall. And what's really cool is, you know how when we were doing free fall at every point, it was just that acceleration free fall, so it was always negative 9.8? Well, it's sort of similar here. It won't always be negative 9.8, or it won't even always be just like the same number across the board, but at every point on an inclined plane, the acceleration is going to be the same. So you see how these arrows, these pink arrows are around the same length? The acceleration at every point along the way is actually going to be the same. So the acceleration down that inclined plane, we can normally say is A is equal to plus or minus G sine of theta. All right? And when we say that, you'll notice that it says plus or minus. However, what that plus or minus comes from is, like we talked about earlier, acceleration is going to have direction to it. All right? So it's all going to depend on which way the inclined plane is facing. Here, when you're going down, you're going to the right. So your acceleration would be positive. If the inclined plane were turned the other way and it were going downwards, it'd be going to the left. Then our acceleration would be considered negative. So it all depends on which way the inclined plane is facing. Then there's another thing just to cover really quick. So I remember when we talked about it on our math review, some of us were a little shocked. Remember when we had an object on our inclined plane and it had sort of like this angle going on, and I wanted to know what this angle was, and I said that that angle was always going to be the same as that angle? That is still true, and there's another one now, okay? So what we have now is that we have acceleration acting in a few different ways. We have the acceleration of free fall, which is going to be acting straight down on our object. We have a parallel acceleration that's going to be acting parallel to the ramp. And we also have a perpendicular acceleration that's going to be acting perpendicular to that inclined plane or ramp. So we have our acceleration free fall, our acceleration parallel, and our acceleration perpendicular. And this angle right here, this theta, is also always the same as that theta. So this theta will always be the same as that theta as well. So you've got two thetas that are always going to be the same. And that makes your math really convenient, because once you find one theta, you've got two other thetas now. All right, so there's just one last thing I want us to do today. And that is, I want to draw a picture of a track, and I want us to draw the position, velocity, and acceleration graphs for it, okay? So, straight, down, straight. We have a ball, and it is going off with some V0 that is greater than 0. And it's going to follow this path, all right? We don't need to label any times or anything like that. I just want us to look at a general breakdown of these sections 1, 2, and 3, okay? So that will be our position versus time. This will be our velocity versus time. And this one will be our acceleration versus time. Okay, now let's break up our sections. Okay. Now that we have our sections broken up, what is the position going to look like in section 1? Okay? In section 1, it will just... All right, now that we have these sectioned off into sections 1, 2, and 3, let's talk about what each graph will look like. So, for position, in sections 1 and sections 3, it'll be following a basic linear progression, right? because the slope of position is velocity, and it's going to have a constant velocity. But right here, what's it going to be doing? What's that A word? It's going to be accelerating, which means it's going to have a change in velocity, which means that its position is going to be a little curved, okay? Then we're going to come over here to velocity, all right? We normally assume that at flat places, we're going at a constant velocity, all right? So we know that the initial velocity is higher than 0. And then when it gets down here, it'll start going pretty fast, because in this section in between us, it's going down the ramp. We're going to see an increase in our velocity. And then finally, with our acceleration, at these horizontal planes, there's not going to be any acceleration. However, we will have acceleration the entire time we're on that inclined plane. We will have a constant acceleration. All right, you guys, that was our last example for the day. Remember that we're going to do 1 or 2 examples in class tomorrow together, and then you're going to be working on a problem set, all right? I just want to remind all of you that if at any point you start to feel like you're overwhelmed in class, or like you haven't really learned what you're supposed to, I'm always open for tutoring. I tutor every day before and after school. I do it based off of your schedule. Just reach out, just let me know, and we will make sure to get you where you need to be, all right? Thanks so much for watching. I'll see you guys tomorrow.